16.2 talks about line integrals, and we're going to start by sketching roughly what we already know. So here I notice the x and the z are fixed at 1. So we're stuck right there. And it seems t is the only varying value, which is the j. At 0, we are at 1, 0, 1. T equal 1. If you really must. And t equal 2. So what's important here is that you get the direction. The graph is only the purple part of what I did. Everything else is for reference. You're welcome to reference this any way you like. If I look at the next example up, here I notice that this is actually k, 0, 0, t. So I am stuck on the origin. The only points are going to be at -1, I am right here. At 0, at 1, at 2, and at 3. So pretty much I'm just going to follow and make sure that you mark the arrows. I should have did that here more clear. There you go. And if I went to that example right there, well, I'll notice here there are a couple of things going on. So this is ti, 0, and 3 minus t. Well, at 0, I am at 0, 0, 3, right? That's r of 0. Maybe I should do it this way, that's better. Be more efficient. And r of 1 is going to be 1, 0, 2. And r of 3, since it's a straight line, I know what that looks like. That's going to be at 3, 0, 0. So, if I mark my points, 0, 0, 3, I start right there. 1, 0, 2, and 3. So I know that I'm tracing along this line, and it's running in this direction. And it's only a line segment. This is not array. This is not infinite. And if I look at the last one, well, I know what that is. R of 0 is really 3, 0. Sorry about that. I missed a point. Actually, 2 points. I'm going to alter that slightly. Let me fix that and come back. Okay, all fixed. And r of pi over 2 is really 0, 3. So if I look at the points, this is, I know that's the I and that's the K. So there's the I, there's the K. And 1, 2, 3, 1, 2, 3. At 0, I am right here. Pi over 2 units of time, I am right there. And I know that's a quarter of a circle. So I'm running in this direction. And there it is, done deal. Now, to find an equation of a line using parametric equation, a line segment, a piece of a line, take the beginning and the end, and you could use this formula if you like. I normally use intuitively, what I learned from parametric equations, but you could use whatever you want. And in this case, if you use this, the limit on t would always be t between 0 and 1. Now, if I look at the next line up, which is line integrals in space. Suppose that C is a smooth space curve. Define parametric equation where t is varying between a and b. Then the line integral of f of xyz ds. Well, you just plug that in, that in, that in. Let's get ds out of the way. ds is the square root of g prime of t squared plus h prime of t squared plus k prime of t squared dt. We get that from chapter 10, parametric equations. And if you look closely, you would notice that this is actually the magnitude of r prime of t dt. So this ds right there is actually the magnitude of r prime of t dt. And they really like this notation. Instead of saying substitute the I for the x, the j for the y, and the k, they say, why don't you just evaluate the function f at this vector? What they mean, the I in the x, the j in the y, and the k in the z. So the idea is fairly simple and really straightforward. Evaluate the line integral. Now, what does this really find, by the way, just to demonstrate really quick? This would be, if you are looking at the curve C, you know, where C is, a smooth curve. What it does, it really traces the different heights of C and gets you that area. That's really what it does. If you really want to know what this is finding, right, this would be the integral of f of x, y. That would be the height, actually. Right, that one right there. And if f of x, y, z is positive, then pretty much it's going to figure out the area of that fence. Alright, so how does this work? Well, the line integral one, looking at this, I could write this as, remember, r of t and parametric equations go hand in hand, so I'm going to say 2t, 3t, negative 4t, if it's that simple, and have t run between 0 and 1, that will work. At t equals 0, I am right there. At t equal 1, I am right there. And it's linear, so this integral will equal 0 to 1 because I already found that. And how does that work? What's x? X is 2t. What's y? 3t. And what's z? Negative 4t. And what's ds? Well, that's something you need to find every time. You go on the side and say, alright, well, let's see. R prime is actually 2, 3, negative 4, and magnitude of r prime is the square root of 4 plus 9 plus 16, that's 29. And that's how it's going to work on each of those. So this is going to be the square root of 29 times the integral from 0 to 1. 2 plus 6 is 8. 8 minus 12. 8 minus 12 is negative 4, I believe, if I'm not mistaken. And you could go from there. Again, if the function is always positive, then that would be the area. Otherwise, it's going to find something else. How about this problem? Well, the same deal, actually. If you think about it, in this section, they're really straightforward. That right there is the integral. Well, they gave us r. I don't have to find it. X is twice the cosine of t. Y is twice the sine of t squared. And ds, if I take r prime, that is negative twice the sine of t twice the cosine of t. And if I take the magnitude of r prime, that would be the square root of 4 sine squared of t plus 4 the cosine squared of t. If you factor a 4 out, that is sine squared of t plus cosine squared of t, which is a 1. So this is a 2 times 2 dt, and t varies from 0 to pi. Nothing to it. You're done. You integrate that, and That's pretty much it. And any of these examples, if you'd like me to integrate them in class, ask me. I'll be more than happy to show you. You're responsible to integrate everything, even though I'm not integrating because that's a prior course material. How about this problem? What if I have multiple paths? What if I want along C1, C2, C3? So if you call this C sub 1, C sub 2, C sub 3, we say integrate over the path that's going to be the integral along C1 plus the integral along C2 plus the integral along C3. And here they gave us the equation. Normally you have to find that. That's going to equal the integral. The first piece, that is 0 to 1 of what? Again, this is the function. So here I noticed that r is actually t0, 0. So t plus 0 squared minus 2 radical 0. And what's the magnitude? What's the derivative of that? R prime is 1, 0, 0. So the length of that is 1 dt plus the integral from 0 to 1. When I get to the second piece, I am looking at r being 1 t 0. So r prime is 0, 1, 0. So it's going to be, again, I'm going to put a 1 for x, a t for y, and a 0 for z, 1 dt, plus 0 to 1 along r3. R is actually 1, 1 t, and r prime is 0, 0, 1. So they're all nice. The length is 1, but here I'm going to take 1 in for x, 1 for y, t for z, times 1 dt. And there it is. And you could combine those if you wish because they're all 0 to 1. That is t plus 1 plus t squared plus 2 minus 2 radical t dt. On a test, if I say Sarah do not solve, this is sufficient. That's all I want you to do. And you could finish this problem on your own. Integrating should be something basic for you. How about the next problem? Well, here they're kind of giving us this slightly different. Well, not a big deal. They want us to go by a circle with a radius 3 from 3, 0, 0 to 0, 3, 0. Take that path. We know what that is. C1, we're going to say on C1, let r equal 3 the cosine of t, 3 the sine of t. And if I have t vary between 0 and pi over 2, I got it. And a line segment from 0, 3 to 4. That line segment. Well, this is how I do it. Y equal m. M is you are at 3. You go up 3 and you run 4. So rise 3, run from 0 to 4, x plus 3. So I should say C2. This is how I normally do it. It's very simple. Let x be t and y will be 3 for t plus 3. And here t varies between 0. I am at the point 0, 3. And x equal, what did we say? So since I let it be x, 0 to 4 will do. That's how I do the problem. you're welcome to use that formula that I mentioned. And this integral right here will be the integral along C1, which is 0 to pi over 2 of what? Of x. X is 3 the cosine of t times, what's the derivative of that? That's negative 3 the sine of t plus the y squared, that is 9 the sine squared of t, times dy. The derivative of that would be 3 cosine of t dt. That part is done. Plus the integral along C2, I'm going to run that from 0 to 4. And x is t. And what is r prime? Because I need that. 1 3/4. And I should have did that here. This way I've not put it in my head. But dx is 1 dt plus y squared. Y is 3/4 t plus 3 squared times 3/4 dt. Evaluate that, and there it is. We're done. Now, when I have a vector field, now we're getting to more theoretical parts. If I look at a vector field and I figure out, let f be a continuous vector field on a smooth curve C defined with r of t, where t varies between 0, a and b, then the line integral of f along C, the line integral of f along C is really the vector field times the tangent ds. Keep in mind the tangent is r prime divided by magnitude of r prime, and ds, oh, that shouldn't be, excuse me, there we go. ds is the magnitude of r prime of t dt. So if I multiply this, if I take this and I put it right there, wouldn't these two cancel out? And what are you left with? R prime. And guess what? Work is the integral along C of f dot dr. That's a big deal for us, something that's never going to go away. And based on what we did, f, make sure you simplify, you replace the I component with the x, the j component with the y, times the derivative, dot it with the derivative. We know how to do the dot product. So when it says evaluate the line integral of f dot dr, they're saying find the work done by moving along C, r from a to b in this specific vector field f. Well, the integral along C of f dot dr is going to be the integral. Here they gave us the equation. I don't have to come up with it. 0 to pi over 2. And now we know how this works. What is f? Well, y, that's 3 the sine of t. X, that's 3 the cosine of t. And x squared y. X squared y would be 9 cosine squared of t times 3 the sine of t. And I'm going to dot that with dr. What's the derivative of that? That is negative 3 the sine of t, 3 the cosine of t, and a 1 dt. So that's going to equal the integral from 0 to pi over 2. And you multiply, that's negative 9 the sine squared of t plus 9 the cosine squared of t plus 27 the cosine squared of t sine of t dt, and that would be my answer. If you evaluate that integral, you're done with the problem. You just figured out the work done in moving along this path from between 0 and pi over 2 in this vector field. And another problem, again, find the line integral. Again, they give me the vector, the line integral along C of f dot dr is going to equal the integral, and you just have to fill in the blanks. Z plus y, that's t cubed plus t squared. X is 2t, and x squared 4t squared minus y. And I'm going to dot that with dr, the derivative of that. That is 2t, 3t squared, dt evaluated from 0 to 3. That would be, again, the work, and that will be the integral from 0 to 3 of 2t cubed plus 2t squared plus 2t, that's 4t squared, plus, and if you multiply those, this is actually 2t squared. So 2t squared times 3t squared is 6t to the 4th dt, and that would be it for this section. So a very straightforward idea, extremely important. We're going to build on that, so make sure you get that out of the way before we move on.